welcome. Thank you for coming, and I would like to first I'll start by thanking you all for coming to the Grand Browns Lecture Series. This is a series that the School of Public Health does 6 times per year, and we select speakers who are internationally renowned in different subject areas, and it's my pleasure today to introduce our speaker who is speaking to us about an area related to environmental health. So I would like to introduce Dr. Mike Bergin. Mike is literally the first person I ever met when I came to Atlanta. Like when I first moved here back in 1999, the first guy who talked to me was this guy right here, and I've known him ever since, been a really good friend ever since. Mike, I should also, in full disclosure, say the reason I met him first is because he's my PhD advisor, and I moved here to start graduate school at Georgia Tech, and when I came for my campus visit, that's who I met. Let me talk a little bit about Mike and give you some information about his background, where he's coming from. Mike is from Minnesota originally. Went to undergrad and master's at the University of Minnesota, where he was studying aerosol science. That might seem a little obscure, but it becomes really important when we hear about what Mike's going to talk about. The University of Minnesota is one of the first universities that really kind of launched the science of studying particles in the air and how they might affect climate and health. From University of Minnesota, Mike got his PhD at Carnegie Mellon University in Pittsburgh, and then did a postdoc with NOAA and NCAR in Colorado, doing a lot of climate-related work. After his postdoc, he got a faculty position at Georgia Tech in the School of Civil and Environmental Engineering. Was at Georgia Tech for 15 years, plus or minus. Then moved to Duke University about 10 years ago. The one thing I would like to say about Mike is that there's no doubt that without Mike's influence on my life, I would not be here doing what I'm doing right now. It's been a big impact on my life, and I know that's true for many other my other colleagues as well. And the science that he has done over the course of his career has really changed how we know about the things that we know how particles influence climate and health in a couple of really important ways, and I'm really excited to hear what he has to say to us. So join me in welcoming Mike to the stage.
Thanks everybody. It's great to be here. Atlanta is my favorite city in the world. I love Atlanta, and I consider myself an Atlantan above all, and then maybe a Minnesotan after that. Okay. So what I'd like to talk about today, first I'll introduce sort of my research interest, but I really want to highlight some themes I'll talk about as we go. Kind of in a big picture, the left there, that's AI, data analytics, and it's an interest of mine, and I'll talk a little bit about that as we go. I'm really interested also in renewable energy. These particles that get in our lungs also, as you can see, deposit to solar panels. There's about $100 to $200 billion a year loss of dirty solar panels. I'll mention that just because I think it's really interesting. What I'm going to talk a lot about in the lower left is the development of low-cost sensors, which I think this DIY related things have really helped us in science and engineering and in public health as well. One great interest of mine in the middle is undergraduate education. That's actually a research project with undergraduate students from Duke that we did in China. And one thing I should mention, the lower right corner, I'm not going to talk too much about this today, but I'm also interested in climate and climate change. And I'm from Minnesota. That's a picture at about 11 or 12,000 feet on the top of the Greenland ice sheet. And I also do some research related to really pristine areas as well. Real quick about me, because I think for me, one thing I would say is I think the most important thing in our lives is our connection to people above all else, not what we do and what we accomplish, but our connections and our friendships. And thank you, Roby. Roby has remained a great friend of mine, and I think I've gotten more out of our friendship than Roby has, because Roby was a fantastic PhD student, and some of his research is that I'm not going to talk about today has still stood the test of time, and something I'm really proud of. Left corner, another thing I would say, one thing, Roby was the first person maybe that I met in Atlanta, but one thing that Roby imposed upon me is the beauty of the southeastern United States. I think that Atlanta is the greatest city in the world, and maybe North Carolina is one of the most beautiful states in the world, or in the country for sure. Left, that's the Chattooga River. I love the outdoors. That's fishing the Chattooga River. The middle is kind of where I live. That's my dog and my cat, who are really good friends. My cat right there is from Ormond Street in Atlanta. She was an outdoor cat. And her son lives with us, too. He is also an Atlantan. So we're the Atlantans in the house. The bottom left are my kids. That's at Grandfather Mountain, another place that Roby told me about, another beautiful place in North Carolina. My kids are from Atlanta, and they're Atlantans, and they love Atlanta as well. Middle, my wife. My wife got her PhD also from Georgia Tech with Roby at that time, and she works at the EPA. And bottom right corner, I was at Georgia Tech. I love doing exercise. And one thing that I think, apart from our connections with people that are so important, I've made new connections today, I think it's, I've always said, I think it's really important to lead a joyful, balanced life. And so I think I try to do a lot of things with my family and friends. I try to stay in shape, and I think that has enriched my life a lot. So enough about me and my research. I want to jump into what I want to talk about. I have one thing here for the young people who are faculty members, and template for success if faculty members are working in business. You got to have an exciting problem. You have to have people you want to work with, and you have to have money. And just keep in mind, everybody, those three things, at least in our work lives, are the three most important things for success. Sometimes you can have two of them, but you really want three. So we shouldn't be, I know we're bashful about talking about money because we all think we're trying to do things for the greater good of society, but money is very important too. I want to say that. That'd be a theme. So starting this, this is, I think, maybe what everybody has seen. This is the global burden of disease. On the y-axis, this is estimated deaths, mortality, and these are different models that we're on. You see air pollution, about 7 million people per year. Water pollution, maybe 1 to 2 million. Usually what I say, and facetiously, is that this shows that if you would study anything that impacts health, you'd be studying air. But I think that that's probably not exactly true. I think maybe the water estimates are more uncertain than you would guess. But I think what's really interesting is the interface between poor water and poor air that generally go together. And I think that's a really interesting area of study as well. I'm going to talk about air. That's what drives our interest in air pollution. And many years ago, we started thinking about how to measure air pollutants. Measuring air pollutants this is probably 20 years ago for me. And measuring air pollutants is really, really expensive. This is an instrument that measures particulate matter, PM 2.5, the thing that drove that mortality I just talked about. That's a box that it goes in. Probably costs hundreds of thousands of dollars a year to measure PM 2.5. So maybe about 15 years ago in my lab at Georgia Tech, we started trying to develop low-cost sensors. So let's just put $100,000 on the tab to really make this happen every year. And since that time now, there are many different types of low-cost sensors that measure. I'm going to talk about particulate matter, PM 2.5. There's a lot on the market now, but that has not always been the case. You see on the left, looks like a purple air sensor. That's purple air sensor. But what we did in my lab first is this is probably 12, 15 years ago, is we made low-cost sensors. We made our own low-cost sensors, and you see, it's kind of hard to see, you see those black boxes and then those sort of light boxes. This is on the roof of Peking University. We were working with China at that time to try to understand their air quality problem. We made these in my lab. There was a team of about 15 undergraduate students, postdoc, 2 or 3 graduate students, and it took us almost 2 years to make these sensors. We made them ourselves, we fabricated them, we tested them. And these sensors cost, just the components cost about $100. So we'll just talk mostly about PM 2.5. We also did them for ozone, but PM 2.5, let's focus on that. $100, so this was 3 orders of magnitude decrease in the cost of measuring PM 2.5. And of course, a quick question that you might ask is, do they really work? We've done a lot of work on that. But so, for example, on the x-axis here, this is a federal reference monitor, one of those real expensive ones on the x-axis. On the y-axis are these $100 sensors. And if you look at that, really, there's a lot more to this than meets the eye, but if you analyze the data right, you do the corrections right, you can come within about 10% of that $100,000 monitor. So I wouldn't say quickly, but over several years, we were able to make these sensors and sort of shift things a little bit to these low-cost sensors that work almost as good as those really expensive ones. And in some cases, they even work better. And let me just give you because we're talking about public health here, let me explain this. We made these low-cost sensors. The first thing we did is we did a health study, 40 homes in Shanghai of asthmatic children. And if you look, let's look at that left panel, that's PM 2.5. And we look at the left side of the left panel. What we had is we had filters in homes. So we'd filter the homes for a few weeks, then we'd have washout, then filter the homes for a few weeks and have washout. So what you see on the left there is you see the PM 2.5. That first box was about 40 micrograms per cubic meter. When we filtered the air in the indoor homes, we dropped it almost by a factor of 2 to 15 to 20. So the filtration worked pretty well. We also did ozone in the right panel. I won't talk about that today, but I'll keep it at PM 2.5. There's reasons that ozone is important too. I'll mention that a little bit. And this is the health effects. Now this is kind of hard to understand, but we also did many times during the study, we tested the children. We did exhaled nitric oxide on the top there for airway inflammation. We also did some other measurements of pulse oscillometry for lung functions. So if you're on the left side of those dots, that means that when the filtration took place, it improved health. So this was the first study to show that you could improve health by doing indoor filtration. Indoor filtration is probably hundreds of billions of dollars a year business, bigger than ever right now. And this did show that there's health effects. I think I want to say one more thing about this. Let me move on. But this was a paper that was in JAMA Pediatrics, and a paper we were pretty proud of. So low-cost sensors, 3 orders of magnitude cheaper. Now it opened the door to do lots of different studies of air quality. We were asked by some collaborators in Delhi, one of the most polluted cities in the world. On average, the pollution in Delhi is 400 to 500 micrograms per cubic meter. If you remember the number 10, 10 is healthy. Above 10 is thought to be unhealthy. In Delhi, often, if I was in this room in Delhi, let's see, right now probably in Delhi, if I was in this room, it would look a little hazy in this room. That's how polluted it is there. So we were asked if we could take these low-cost sensors. If you see, we took our low-cost sensors. We took about a dozen of them. We put them around Delhi. Delhi government had some monitors, and they asked us to compare our sensors to their monitors. And one thing I just want to say really fast, and this next slide is very complicated, but I want to say big picture of this slide. So what we did is we took our sensors and we calibrate them, but then we constantly compare them to each other in the reference monitors, and we do on-the-fly calibrations to keep this 10% error there. So we're within 10% of the reference monitors. Now, this just shows, this is an AI model. This is an AI method, and it's a statistical method called Gaussian process regression modeling. I don't really understand it that well. Point of the matter is, though, when you merge AI with, there's a theme. I'll mention the theme now since I didn't mean everybody to laugh because I didn't mean it to be funny, but I'm glad you laughed. Nobody's ever laughed at this part before, but it's true. But I would say the point of this, big point to this, is that I have a collaborator who's an expert in AI. I don't know anything about it, but he's able to bring these super scientific AI methods to my research. And I think the theme is that we all need to have, in public health for sure, we need to make these connections with computer scientists who are experts in AI. We should not be trying to do the AI. We should be working with the experts to help us develop AI specific to our needs, and that's what this is. And I'll skip this, but generally speaking, it worked great. Talking about air pollution, low-cost sensors, we can now put those out in places to better understand pollution and what pollution people are exposed to. But those air pollution sensors only measure at points. And constantly people are saying you're not measuring at the right points. We want to know neighborhood level air pollutants. So we had this idea that you could take satellite images, just the pictures, train those satellite images to the ground measurements, and then make really high resolution maps. Let me explain how this works. This is in China. This is the same picture. In the middle is one of these regulatory monitors, or you could have a low-cost PM 2.5 sensor in the middle. And then you can see, so on the left, 265 micrograms per cubic meter, you can't see very well. Going to clean on the right, 6 micrograms per cubic meter. There's a lot of information in here. And so this is, you know those when you go to the airport and they take a picture of your face and they know who you are? You can take that same information, same method to get all the information in these photos, and then you can train these photos to estimate PM 2.5 in places where you don't have sensors. Oh, and the other thing I want to say about this is we're able to do this because there's these new satellites, like these little shoe boxes I was explaining to people, and they take 3-meter resolution images, at least one place everywhere, every day. So amazing satellite imagery going on. And so this is what it looks like. Again, I kind of understand this, but so for example, the right part is something called a convolutional neural network. Really what that is it kind of just takes all the information in that satellite image and tries to figure out what's unique about it. So this is an AI method. Left is another AI method called random forest that takes a whole bunch of stuff and figures out how they're related. So you look at the picture, you look at the meteorology and the PM 2.5, and then you figure out the trends, and then this thing makes a like super complicated regression model and figures out based on an image what the PM 2.5 is. The way I was able to do this is not because I could do this or my students. I did it because I had a collaboration with an expert in AI. And here's what it looks like. This is Delhi, India. This is probably a 50 by 50 kilometer grid. And what you see on the left there, that's a PM 2.5 concentration. That's a hotspot map using contrast. What you see is all these colors. There's hot and cool, tons of hot spots and cool spots. And in the bottom there, the hottest spots, that's what the hottest spots look like, really urbanized areas. The coolest spots look more rural, like more, even though it's not rural, but they're green space. I actually, to be honest, I thought it would be the opposite, because if anybody's been to India, in India they burn probably 40 to 60% of all their trash and refuse. And so most green spaces in India, in urban areas, are places where there's trash burning going on. So I thought that the green spaces would be more polluted, but that wasn't the case. And I won't talk too much about it, but we know there's a bunch of industrial activity. One of the hotspots is over the airport. So we're able to give the government now, based on our training with the low-cost sensor network, we're able to give the government really solid information about where the pollutant sources are, neighborhood-level pollutant sources. One thing we haven't done, which we probably should do, is overlay this with a population map and then see how exposure would be different if you just take citywide mean values or you take this, population exposure. So that would be a public health connection to this, which we have not looked at yet. Yeah. And I just want to say this is a busy slide. So low-cost sensors, better understanding air pollution. So that we kind of had the ball rolling. We're kind of on a roll. I wrote a proposal to the U.S. State Department, and the proposal was in 10 countries across Central and South Asia to help them lay out these networks, satellite imagery, neighborhood-level pollutants, but work with stakeholders, government stakeholders, to try to move policy. And one thing I'll say about that, and this was kind of new to me, so I just turned 62 years old, so my career mostly was doing research, but I got enough experience and I got lucky enough to get this big project, and I managed about 80 people. It was pretty amazing, and it was the fascinating part of it is when there's that many people, as you guys all know, there's always issues with people. We had people of different religions. We had countries that refused to be on papers from other countries, and it was really fascinating. And it's ongoing now, and it's been a lot of fun, actually. And what it looks like, so now we know how to do sensors. We put sensors all over the place. You see this is going up from Pakistan to Nepal, Bhutan, Bangladesh, the Maldives, Sri Lanka, and India. And what's interesting about that is, I'm going to skip this slide, I'm going to go back real quick. So there's a city in northern India, I think, let's see, I don't know if everybody can see, it's called Lucknow, capital, Uttar Pradesh, the most populated region of India. And so we decided to put, this is a very, very polluted place, so we put our sensor network there. And then here's what you see. So I show this slide. This slide is an example of, I tell students it's a bad slide because it was made by my collaborator in India, and he believes that every slide should be a poster. So, but I just want to show you over here. You see, so here's now the kind of information you get with our approach, though, because I don't know. I'll show you. Over here, we have it concentrate. See, look at 120 micrograms per cubic meter. Even the lowest is about 40 to 20 months. You can track the concentrations across the city. Also, you can kind of see there's a lot in here that I want to. But then you can merge that data with satellite imagery, and this is what that looks like. Again, another poster. But let me just show you the important part. You see that thing that says winter? So what that is the satellite-trained images getting high-resolution hotspots. Then we see these hotspots all around. There's a big hotspot in the middle of the industrial part of town. We didn't even have sensors there, but the satellite was able to show us that's where the pollution's coming from. So we're working with the UP Pollution Control Board, and we're supposedly they're going to try to mitigate some of this by looking at what the sources are. Bottom line, though, is we are constantly watching, and they know we're watching with our satellites, with our sensors, and we're working together with them to hopefully make the air better there. Another thing I want to mention is, so we also are doing a study in the Maldives. You guys heard the most beautiful place on earth, the Maldives. I was actually, as an aside, one of my big disappointments is I had this big project, and I was going to go to all those countries. The second year we had this going, a week before I was walking my dog and slipped and fell, and I tore my patella tendon, and I could not go, so I've never been to the Maldives. I wish I could have gone, but my partners went. And so the Maldives, you can see this is PM 2.5 concentrations, our network across the Maldives. The green means that it's pretty clean. But what's interesting about that, so here's what we learned from this network in this pristine place. We didn't really even want to go put sensors there because we believe the Maldives to be a very clean place. And they're little teeny islands in the ocean. They don't have many sources. But sure enough, here it's a PM 2.5 as a function of time of year. And what you see there, you see in January, February, that there's 40 micrograms per cubic meter. 10 is the clean part. That's really, really high. So it turns out they also do have high concentrations of PM 2.5 in the Maldives. And this is because during that time of year, the super polluted regions of India are pollution's being transported to these places. So the bottom line is, and you guys probably know this, is some places are really clean, and yet they're polluted from transport from often really far away. And now the Maldives government knows this, and they're supposedly in ongoing discussions with some of the Indian folks in India were in the Indian government. But the other thing that we learned, and this is another theme, I'll come back to 2 points in this theme. The left is a satellite image from Planet Labs in the Maldives. You see it's a trash dump that's burning. So it turns out, maybe I learned this, a lot of these island communities, they have to get rid of their trash. And often what they do is they pile it somewhere and burn it. And that's what they were doing. So also we heard the government was getting ready to shut down that landfill. So what we did is we made an AI method with my AI collaborators, like I told you about. And it's kind of painstaking, but we took hundreds of images, and then we had a few of us would go and just trace them. And then the computer learned where the plumes were. And on the right was the computer's guess of what the plume might look like. And so now we have an automatic plume tracker that just watches this site all the time. And the government said that they've stopped the emissions, and sure enough, they have. And you see, what those dots show is it's a dots over time of how many plumes there were, and you can see where that line is where the government said they stopped emitting or they capped the landfill and there's no more emissions. So AI has also given us the ability to track plumes, to watch pollutants, and the theme is for a lot of governments is that we have surveillance all the time now. And so if you said that you're stopping a pollution source, it's really stopped. And I'll say a couple other things. We also have been doing some studies in Central Asia. This is Uzbekistan, Kazakhstan, and Kyrgyzstan. Has anybody ever been to those places by chance? Yeah, so okay, I'm going to make a prediction here. These are going to be the new places where some of you young people start to travel. In the next 10 years, these are going to be heavily traveled places because they're safe, they're incredibly beautiful, and they're cheap. So if you're planning a trip somewhere and you want to go somewhere super cool, there's no beaches. That's the only part of these places. But if you love the mountains and beauty, these places are incredible. The thing about these places is they're high. Some of these places are high, nestled in mountains, some of the main cities. They get really cold in the wintertime, and they burn coal, not just for electricity, but people burn residential coal to keep warm, and it gets really polluted, so that's why they asked us to go there. And this is just to give you an idea. This is Kyrgyzstan across a bunch of different cities in Kyrgyzstan. This is the bluish dots or the bluish bars are the summertime, and the orange ones are the winter heating season. You can see, man, sometimes, gets as high as 250, 300 micrograms per cubic meter. So, well, people there knew this, but we didn't quite have all the data out. But because we now had these low-cost sensors, we could go there, we could document how bad the air quality was, and now we're working with mitigation strategies with the local governments there. I want to see if I can show you this. This is not typically what you want to do, but I'm going to shut this off. I'm going to see if I can keep cool when I do this. I want to show you a quick video, and then I'm going to come back to this. Okay, so I've been asked by some of the students today. Well, first of all, it was great to meet the students, and you guys asked great questions. One of the questions was, how do you might be doing all this air pollution stuff, how do you reach the public? So in Kyrgyzstan, we are working with Move Green. They're a nonprofit organization. This is in Russian. So here's what I want to show you, and then I'm going to run through this. It's going to take about 30 seconds. This is a landfill in Kyrgyzstan, very similar to the Maldives. This thing was putting smoke for tens of kilometers all over the place and exposing tons of people to this burning landfill. So the government said that they were going to fix that landfill. So as they did it, we used Planet Labs. We did surveillance. We watched this landfill and watched it to make sure the government was actually capping it. And now we're still watching it to make sure it's not burning. But check this out. There's a landfill. You see it? Let me see if I can fire this up. And this was a Instagram post that the nonprofit Move Green that we work with posted. Okay, you see. Okay, you guys see all the smoke coming out of there? You guys see that? And this is 2020, right? Got it. See that? Smoking all the time, right? You guys saw that? Kind of go through winter time. It gets really cold there. It's still smoking. Okay, look at this. Uh-oh, they're starting to cap it. You see that? Oh, winter time. Okay, there. So look at this. Oh, they're starting to cap it. Looks like it's capped. Now we're dumping other stuff on there. I don't know what that's all about. Chinese building this thing up there. The Chinese company came in and did this. So over time, we're watching it. Cap the whole thing. It's not smoking anymore, and we don't. Hopefully, they're not burning the stuff somewhere else. But again, the point of the matter is we can do surveillance with satellite imagery. People ask me today what kind of data do I love looking at? I love looking at the air quality sensor data. I look at the satellite data all the time, and I look at MET data, which I'm going to talk about in a minute. Again, and then this was really good because this organization, the nonprofit we work with, used this to say the government is doing a really good job. They capped this, like they said, and it's not smoking anymore. So then it forged this closer ties with the nonprofit and the government. Okay, now let's see. See if I can get back here. Okay. Okay. A couple things I want to mention. I want to move on and talk about the last. There's one more theme I want to talk about. So sensors, outdoor air quality, surveillance, working with governments to make the air better. I think what the next important thing is for those of us studying air pollution and environmental exposures is heat. Okay, I think this is going to be the most important thing in the U.S. because I think, well, two things. What I think is important is heat. That's Durham over there. That's a high-resolution map of the temperature in Durham that we've made. I'll talk about that in a minute. Heat. One thing I want to say about that high temperature, well, I'll come up to that in a minute. Temperature in Durham, temperature map, and what I think the combination of heat and indoor air quality exposure, heat stress and indoor air quality exposure is going to be what's really important moving into the future for us air quality experts. And so that we have a project in Durham looking at homes and the combined effect of heat stress and indoor air quality exposure. And I was going to skip this, but I'll talk about this briefly. The thing about indoor air exposure that is not well understood is volatile organic compounds and all the emissions and all the different compounds that are emitted, their toxicity and how dangerous they are for us. This here was in India, but I just want you to look at the top two. This is summer and winter in India. The different colors are different sources of VOCs. You see that orange on the right there? So that orange is like a bunch of plastic emissions in the summer. That's probably a lot of plasticizers and things like that, and things coming from probably additives to furniture and things like that. So, but then in the wintertime, all the colors look a little bit different. Ends up being more cooking, but the point of the matter is when it gets hotter, the emissions look different, but the emissions look different home by home. So we're admitted, so at least this is in India, but also here, these VOCs play probably a huge role affecting our health, but it's not very well understood. And they vary depending on season. So that's one thing I think is an interesting area of study and something I would encourage everybody to look more into. And the reason heat is so important, I think, is heat has huge health effects because, of course, talking about people about public health, and you guys know probably more about public health than me, but it's been estimated that almost 1% of our GDP is affected by heat exposure. There's the direct healthcare costs, there's worker productivity costs, and then there's energy, okay? So heat is really, really important, has a huge impact on our economy, huge dollar impact. And one thing, so I'm gonna come back. Three things that I like thinking about: data, I like the satellites, I like the low-cost air quality sensors, but I haven't got to probably the most interesting and important sensors that at least I love looking at, and I think are going to be important for all of us in the future who study public health, is weather monitors. So this is on top. You see that's Duke Chapel. The one box in the middle, that's an air quality PM 2.5 sensor. We don't make our own anymore. We buy them. And this right here is a Weather Underground. The Weather Underground was the biggest citizen science endeavor in the world. Tens of thousands, maybe more than 100,000 weather sensors. These are the Weather Underground citizen science sensors all around Durham. These sensors give us the ability to estimate heat stress and heat because we have high-resolution temperature information. So what we've been working on is, first of all, trying to figure out what the maps are of temperature across an urban area like Atlanta. Believe it or not, it's very complicated. It's not well understood what the temperature across Atlanta is. I'll make a point about that in a minute. And so here is Durham. Oh, on the right, I just want to show you. This is the Weather Underground stations in Durham. I mean, there's a whole bunch of them. These are citizen science. And on the left is the difference in temperature of right outside Durham to Durham, the mean temperatures in Durham. That's the urban heat island effect, right? So you look in Durham, like if you look there, that's probably right about January 8th. There's like what is it? It's about a 12 C temperature difference between just outside the city and in the city. So that is huge. If you look at the heat stress calculations, it's almost like an exponential increase in health effects when you get, go from, maybe like say 90 degrees to 105 degrees, okay? That's kind of what this is. So, but the thing is, if you look real carefully, like around here, this is actually the most urbanized part of Durham. There's no measurements. And the reason there's no measurements is because mostly affluent people put these sensors in, but they're not in lower socioeconomic areas. And one thing we've done, so one thing we've done is we've taken all this data, the Weather Underground data. We've used a bunch of AI methods to get really high resolution heat maps. This is North Carolina. This is just an idea. This is some of our early measurements. That's in Charlotte, and that's in Durham. And again, what you see, several degrees difference in these cities depending on the day. We've aligned it with census tracts, and now we're trying to figure out how this relates to health impacts related to heat. But the long story short is it took a lot of work to get these maps. Estimating heat and heat stress is very complicated. But again, working with people who study AI, we're using the satellite imagery, meteorological stations, land use estimates, and then we're able to get these really high resolution maps now and figure out where people are being exposed to heat. And And with that said, again, since we're in the School of Public Health here, I guess I talked last night with Karen, who was telling me she's interested in these tracking monitors. One thing we were trying to do is figure out how to track people's health impacts in a cheap, non-invasive way. So we're using these Oura rings. Do you guys know about these at all? The Oura rings, yeah. There's other ways. There's Fitbit time monitors. I like the Oura ring only because I personally hate sleeping with something on my wrist, and most people will wear these. And it gives us a bunch of different data. It gives us, you see sleep. It tells us something about sleep, body temperature, heart rate variability, movement, exercise. So we're trying to figure out, so we have this study now. We have homes doing a pilot study in Durham. We're looking at heat stress, exposure to indoor air pollutants, and we want to track somehow a health effect. So our hypothesis is that these rings will allow us to figure out if there's any impacts of those things on people's health by looking at the data that comes from them. So we're just starting that, but here's kind of what it looks like. This is just, let me see if I can explain it. It's super busy, but the overall theme of it is on the top there, you can see biometrics. It says that's like an Oura ring score. This is over time. This is one person last July to till almost November. Then we have exposure. That's the PM 2.5, and again, there's blips in that. It varies depending on time of day and time of year, and I'm not showing it varies house to house. And on the very bottom is the temperatures that people are exposed to, and that varies as well. So we're just this is all new. We're just starting to look at this data. We have a lot of it. We're holding high hopes, though, for using this data to better understand how environmental impacts affect people's health. We're brainstorming all the time how we can come up with cheap ways, simple ways to figure out if people are being affected by the environment. One thing we came up with was looking at facial recognition. So maybe this gives everybody the willies, but we put cameras like in the student union, and then we take pictures of everybody's face walking by, and then we try to figure out if they were happy or sad. And then my dream was we're going to put these in very polluted places that vary a lot, and then see if the pollution affects people's moods. So for example, this is in our student union, and this is kind of what we came up with is the joy distribution, right? And I always show this at Duke, and we talk about this today. For some reason, everybody in America is so preoccupied and doesn't seem happy, and this reflects that. So I guess that's a lot. That's 700 outcomes for very unlikely that people are happy, and a handful. If we do it again, I was gonna say that I'd get a whole bunch of people and we just go smile in front of the thing a whole bunch of times to see if we can make it a bimodal distribution. But I think, but I think the point is that I think joy is probably the most important thing above even maybe. I was thinking about this the other day. I wonder if I gave you the option, you could be happy or be asthmatic. What would you choose? You know, right? I think I'd probably choose to be happy. No, in other words, no. You could be happy with asthma. No, let me take that back. You could, if to be happy you had to have asthma, or you didn't have asthma but you were sad, you know, I would choose having asthma any day. I think. I don't know. I don't have asthma. My son has asthma, medium asthma. So I know what that. Not bad asthma. I mean, like, you know, this kind of asthma. So okay. So let's see. Where am I? Oh yeah. So we come to find what's interesting. So we were doing all this. This is really cool because what did you take an image, then you do facial recognition on that image, and what we do is we'd store that image. No, we would do the analysis and then throw away the image because of IRB. And we come to find that there's companies that do this in places like Walmart and Kroger and these places. A lot of these places probably have these cameras. They're probably doing it, and they look at how different interventions and trying to sell you stuff, and they want you to have a positive experience in their store. So there's companies that do this and do exactly what we were doing. Be aware. Okay. So lastly, I want to talk about something just slightly unrelated that I like because it's just fun. I want to talk about the solar energy stuff. I just want to say this was started in India. These are solar panels in India. And if you look, we cleaned them off, and it's solar powered production, and you can see that whenever you clean them, the solar production doubles. I remember, I'll just say my friend here in India, he studies air pollution too. And I said, hey man, these panels are dirty. And he said, what are you talking about? And then you can see I wiped my hand right there. And he's like, oh yeah. And I say, hey, can you clean them a few times? So we started this project, and they were showing these huge jumps. After a month, you would lose about 50% of the production in that particular place. And part of this is, again, we're talking to some of the students about this. These were trash refuse burning in India. These are samples collected right at trash and refuse burning in India. These are filtered. All sorts of different colors. The colors are related to the toxicity and sources, right? And if you're interested in this, I would say one thing about it, because I know Roby's interested. There's black ones, and there's less black ones. And what's real interesting in the atmosphere is this is called brown carbon, and it has much different characteristics, optical characteristics, but also toxicity characteristics. And that's the stuff that's depositing to these solar panels. Different colors. It's really cool. And if you look at the surface of a solar panel after about a month, this is an optical microscope image. That's the raw image. That's just black contrast. You can see it. This is a huge amount of particles depositing. These are pollution particles, dust particles, all sorts of things. And what's really interesting, I just want to leave this because, again, we're talking about this is not really public health, but it's related. This is North Carolina. And that's me doing some real work for once. And yeah. And see that swab? I just swabbed that. That's black. Does anybody want to make a guess what that is? Black swab, North Carolina solar panels. Where do you think that comes from? Anyone want to make a guess where that might come from? We need at least one guess. Yeah. Oh, that's a good guess. So it could have came from local people smoking. No, that's not what it's from. Yeah, good guess though. Another guess? I got 3 of them. I would guess 3 things. I guess wrong. Plants nearby. Why do you say that? Yeah, because plants can make. Oh, power plants. Oh. I was going to make up a story so you sounded right and say that plants make gases, they can make particles that get on there. Power plants. Yeah, no. So I thought what it was from, normally what we'd say is this is from combustion, like power plants or like farm equipment, right? But, we're out there. We know it's so clean, and that's not what it's from. I did not guess right. What it's from is, if you look close, this is where it's from. It's mold and fungi. They grow on the surface of these solar panels. It's really wild. And I mean, these are like extremophiles because it gets almost 150 degrees, 160 degrees on these panels. And you can PCR that and look at what it's made of. This is just the abundance of these various fungal classes. The black ones are fungus that is black in color. So at least, interestingly enough, solar panels not only are they collect particles, but also, man, weird stuff grows on them. And it's about a 10% reduction in solar energy production. It's about $300 million a year in the U.S. estimated. Okay, I got 2 more things I want to say, and I'm going to be done at 45. That's what I was shooting for. Okay, one thing I'm proud of, and I want to mention this. I want to say something provocative and give some advice. So this is something I'm super proud of. Actually, we have a startup company. My startup company does data analytics on solar panels, looks at them from space, figures out how dirty they are, and then we do economic forecasting of how to optimally clean the solar panels to save a lot of money. Upper left corner is one of my PhD students. Upper right corner is a student who is an undergraduate at Duke, a freshman who worked in my lab her sophomore year onward, and she's one of the founders of our company. We're doing pretty good. And what I want to say is I think everybody, young people here, I think it's really important to have an entrepreneurial attitude. I think this is right, Robbie, this is all the professors, this is what you have to be successful as a professor, because as a professor you have a small business. But everybody, I would tell everybody should be brainstorming how they can start a startup company that's going to have an impactful effect on people's health and the health of the environment. Everybody should be thinking about that. Because I don't know where the future is going, but if you can come up with a good idea that could change the world, and you can make money, remember that third thing, money, it's really important, and make money, then you can be your own boss. It's really hard work, but I think it's the startups of the world that really are going to change the future for young people. So I'm proud of this. I don't know where it's going, but I love thinking about it, and I feel like something that I did is going to come of something. You know what I mean, right? And so second to last slide. What I think is, I think in summary, and I should have changed it, this interface of deep learning, machine learning, I think, and environmental public health is crucial. What I suggest to everybody is, I think we have to learn a little bit about it, but I think we want to find collaborators, computer scientists who will help us and work with us and be our local experts on that. I think maybe I would put another circle that would be internship, or entrepreneurship. Entrepreneurship there too. I think that everybody needs that attitude. That attitude is a dynamic attitude. It's an attitude that makes you think a lot. Part of entrepreneurship is you constantly have to ask yourself, why am I doing this? Why is it going to be a benefit? How's it going to work? And I think that's a really way to think about things in life. I think it's very helpful for our job. So I'm going to stop there. I'll just say there's tons and tons of people that are involved in all these slides. I'll just keep that here. And I think I'm right on time, and I'd love to take questions. Yep. Yep. You can yell real loud too. I can hear you. I can repeat. I'll repeat. Okay. Yeah. That's a good question.
Thank you for your talk. My name's Christine. I work in the school with Roby. I agree that this is the future. I would like to contemplate how what are the negative potentials for AI, both exacerbating disparities, worsening pollution, sucking up our energy and water, and then burdening the people that we might want to be helping. So I don't know if you could.
Sure. I know your question. I say that. So the question was, what are the broader implications of maybe the life cycle analysis of AI, kind of, right? So this is a great question. The students brought this up too. So I want to, and I just came up with this idea that I'll explain it this way. To me, there's 2 types of AI. So on one hand, there's the AI that's the random forest convolutional neural network methodologies that we can use to help answer important questions. So that's I'll call that the scientific AI, and that's the AI I'm talking about. Now, then there's the AI that we all know about, which is get on ChatGPT and ask it a ton of questions. And I think my guess is, and that uses tons of energy, tons. I'm guilty of it too. I'm trying to draw back from asking ChatGPT about what kind of shoes I should buy and stuff. But we do that all the time, right? I do it. So I think that scientific thing is a no-brainer. We have to go that route. I also believe that the AI being used for scientific applications that will benefit society, at least now, and I don't know if this is true, okay, I'm going to say this, I haven't fact-checked this, I haven't thought it out, but I think that sliver of the energy use and impact is teeny compared to all this other maybe not totally necessary AI, right? Does that make sense? We also are thinking deeply about watching these we're watching these places where we're curious about the climate impacts and the water impacts, so we're also kind of looking at that stuff. But I believe that the science part of it is only a small slice of it. I am worried also about the massive use of AI for almost everything now. I think we have to be careful about that. Yeah. I don't know if does that answer your question? I mean, that's my opinion about it.
Hey, my name is Jaden Hightower, and I'm a senior public health major at Georgia State. And my question is, so I was reading an article from the Southern Environmental Law Center, published on June 17th, 2025, and it's basically an article about like Elon Musk's AI facilities is affecting minority populations in Southern Memphis. And I was just wondering, like, so whenever you do like your research regarding AI, like, is like do you consider like some things like how it affects like populations and like minority communities in the U.S.?
I think about it a lot, but I would also say a couple things. The AI our AI models that we run, and we're typically running, and I guess at the end of the day, maybe it's no different, but we run them on our own computers. You know, they're not, I guess we use Amazon Web Services to store all the data we generate. Yeah, we discuss it. We discuss trying to do things. Again, the only way that it works for me is because I have computer scientists, and they are constantly trying to figure out how to do things in a really efficient way. So I would say we talk about it. We're concerned about it. For example, where we do all our computing at Duke, we're really curious. We're looking at the energy consumption and its effect on our localized environment just as a case study to broaden out. But we also talk with our students a lot about the fact that separating this research AI from your personal use AI, so I think the personal use AI is probably the thing that is going to have a bigger impact. Again, that's what I said. And we do worry about it. Yeah, I mean, we do try to minimize our use of it, I would say, or our computational resources for it. We're doing the right thing or enough of it. I don't know the answer to that one. Yeah. It's on our minds, though, for sure. It's a good question. Yeah. Oh, yeah.
So I'm fascinated by the facial recognition and joy and mood. And I know a lot more about it, but I'm wondering, it also like raises questions in my mind about like not just like how mood is expressed in your face, but more behavioral indicators like aggression. Also thinking about like maybe not in a university context, but more like child development outcomes, those types of things. If you've thought about those types of applications.
Yeah, I guess the question is like there's not just facial recognition. There's all sorts of other ways that people hold themselves and move. And we thought about it. We thought that we'd like to connect with more people who are interested in that. We thought about like for example, there's at Duke. I know there's some research going on about autism, and they can look at how children move and behave and facial recognition, combining everything, and then they can figure out, if they early on, if maybe where people are on the autism spectrum is my understanding of it, and then maybe that gives you some way of trying to mitigate some of the effects, I guess. So we thought about it. We just have not connected with the right people. I'd love to do that. Yeah. So there's way more. Bottom line, there's way more to the imagery and people's images that can be, I hate to say it, mined for both mental and physical and health effects. Yep. Super. We've had those discussions. That's a super cool idea.
Thank you for your talk. Great. My question is about your models. So the world is becoming more and more polluted.
Yeah.
Your models haven't seen all of the potential images, right? Do you need to recalibrate the models at some point, or do you do that systematically every year? Or?
Good question. So the question was so you go and you train these models. So the AI approach just memorizes what one place is like and how things change in that one place. And the question is, can you bring it elsewhere or that same place? Yeah, so we're working on it. We've trained over a whole bunch of different places. We don't quite know yet, but what we're trying to do, the computer scientist guys are writing these wacky papers about this that I'm actually not on because I can't understand them at all. But the idea is, like in the acknowledgments, And what they're doing is it's trying to make a generalized model where you don't have to train anymore. So we're moving towards that. I don't know if we're going to get there, but they think we're going to get there. In other words, we have this canned model that anybody can use with satellite images to tell them what the high resolution PM 2.5 is in their region. That's the ultimate goal. Yeah. 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 No. So right now we can't do it. It's a big problem. But what we keep doing is we keep training in one location and then try to use it in another one. And so far it's working pretty good. Even some locations will look a lot different. But I don't know if we're going to get there. That's the ultimate goal. Yeah.
Right. So something that I think about a lot is trust when we're collecting all of this data. And I think, you've kind of alluded to it and joked about the amount of data that we collect and the extent of surveillance. We say, we're watching to see what's happening. So how has trust come up in these projects, and how do you maintain that and build it into projects?
Yeah. So well, of course, on one hand, we have to do this, a lot of this through IRBs. On the other, and I would say, I'll say something that's a little bit of a brag on my part. So I've been doing projects since the late 80s, foreign countries, and the template that we've had in the foreign countries, and so I think your question is like a lot about surveillance in the foreign countries, probably right. Not as much in the U.S. I'm worried about the U.S., but because, it's harder. I'll say this: it's a lot harder to do these field studies I'm talking about in the U.S. for many reasons than in these foreign countries. So we carefully choose the right partners and the nonprofits who work with the governments, and then we let them be the boss. They're the boss. They decide how things are going to work. We do IRBs with them, and I would say that my success in all of this, and why I got that huge State Department project, is because most of our projects have worked out. And with respect to trust, it's really difficult. I've heard this over and over again. People say it's really difficult to do projects in foreign countries. The reason is because we go into foreign countries with we're experts, we're going to tell you what to do, here's how you're going to set this up, local university, this is what you're going to do, and that never works. And because it doesn't build trust. So I think building trust is a key component of this, and the component is choosing the right partners, letting them be the bosses, and even you can't have them make unethical decisions, for example, you know what I mean? Like they can't do things that you would find wrong, but my partners often did things that I did not want to do. I felt were not the right scientific things to do. And I felt took us in directions that were counterproductive to our goals, but that's what they wanted to do. So, I don't know, that's a long-winded answer. Yeah. 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 Yep. Yeah. So how do we ensure that the data is being given to the public in a responsible manner? So, so first off, again, I'll get back to what I said before. Our partners are the bosses. Our part in this is that we're the experts, and we're going to generate data that is accurate and precise and you can trust. I also could intervene if I think the data is being used in a way that's manipulative. Also, I would say this. I'll say something really provocative. I don't believe giving data to the public is always the right answer. I'll give you an example, and it first started with the EPA here. So the reason, when I was getting into this, one of my past students, Gail Hagler, was at the EPA, also working on this together. And the reason the EPA got interested is because people in the US were buying these sensors that didn't work. Like we knew we were testing them on my lab and like, oh, this one doesn't work. Oh, this one's terrible. Oh, this one just gives huge values all the time. And so the EPA was getting calls saying, you've got to come into my backyard. I bought this sensor on Alibaba or Amazon. It says the air pollution in my backyard is terrible. My neighbor's a jerk or whatever. You've got to come and see this. And they were getting deluged with this information. So, and as an example, also in India, in Lucknow, that sensor was not public. My partners work with the local pollution control board, and they said, we want to know better where the pollution's coming from. We want to understand the sources, We want to try to make the air pollution better, but we do not want to give this to the public because we don't want a public outcry of the data. And we don't want to get into this debate if the sensors aren't working or not. So what's interesting, I'll just leave that for you guys, is so it's not always best to give all the data out, even if it's good data. I believe that to be true. Personally, I would like the data always to be public if it was me, but I've been involved in situations where it's best not to make it public. Yeah. Can I take one more question? How about one more question? Someone's got to come up with one more question. Yeah.
The pollution patterns or distribution wasn't as well understood in Atlanta.
Yeah.
Can you expound upon that a little bit more?
Oh, yeah. I meant that heat.
The heat. Okay.
I would argue that there is not a good estimate of heat stress in Atlanta, high-resolution map. And the reason is because those estimates are very difficult to make. There's sparse measurements of temperature, relative humidity, and irradiance. And we know from some of our measurements that there is 10 to 15 degrees C difference. You can go a neighborhood over. But we just don't have that high-resolution measurements. The physics models that are used which people often use, these physics-based models to estimate temperature stress, they just don't work very well. They don't work very well because of the chaotic nature and the turbulence and stuff like that, and the kind of unknown heating and shading that happen locally in urban areas. So we probably don't know. We're working on Atlanta, but it's probably not really well understood what the heat stress is in Atlanta. On average, you might have a number, but because heat stress is kind of an exponential thing, a couple degrees has a huge effect on people's heat stress. I don't think we know it very well. I might be wrong. If there's data out there, I'd love to see it, but that's my opinion on it, and that's what I've seen, at least scientifically. And that's why I think it would be such an exciting thing to look into that in Atlanta. Yep. I think that's it, everybody. Thank you. Yep. Yeah. And please, anybody, if you want to contact me, I'd love to. And I love Atlanta. I would love reasons to work with people at Georgia State. So I would love to hear back from people, or I'm around today. I would love to talk for sure. Yeah. Sure.